With the world eager to adopt renewable energy technologies, the vexing problem of how to store this energy for when the power grid most needs it remains a technical challenge. Dr. Natalie Smith talks to us this morning about a possible solution for this issue. The world's first pumped thermal energy storage demonstration system built right here on the SwRI campus. Natalie.
Good morning. I'd like to start out with a simple question. How do we get to net carbon zero by 2050? Companies and countries around the world have been making goals to reduce their carbon dioxide emissions, as well as operate in more sustainable ways between now and 2050. Many of the proposed solutions include an increased use of renewable energy. Let's look at what that actually looks like. Let's consider the electricity grid. Here, we're looking at ERCOT, so the Texas electricity grid. Its generation mix dating back from 2007 up till last year. You see coal, natural gas, nuclear, and what I want you to note is that we've been seeing an increasing trend of the contribution from wind and solar. In 2022, that contribution was nearly 30% of that generation mix. That increasing trend of high penetration of renewable variable energy is going to move us towards that 2050 goal. However, it's going to, as we continue to increase in this contribution, we're going to begin to see grid reliability issues as we struggle to use solar energy when the sun's not shining and wind energy when the wind's not blowing. So how do we do that? Energy storage is part of that solution. There are two key parts of energy storage that I'm showing on this chart. Along the x-axis is its rated power. So we're looking at kilowatt to gigawatt, so toaster to city power. And then on the y-axis is its duration from seconds, so very fast response, all the way to seasons. How do we go from summer to winter? There are a lot of technologies out there, but let's look at a simpler view. Batteries have entered the commercial market for the short durations, typically meaning under about 4 hours of energy storage. The powertrain engineering division here at SwRI is working a substantial amount in this area, everything from their electrical vehicle work all the way to the collaboration with CPS and the solar installation on the south side of campus. However, the economics of batteries breaks down as we start to move towards longer durations, 6, 10, 20 hours, months. And so to go to these longer duration energy storages, we need different technologies. We're looking at thermal and mechanical technologies for those hours and days, and then moving into hydrogen and other thermochemical technologies for seasons of storage. The machinery department here on campus has become a world leader in these longer duration energy storage technologies. We're working with a multitude of various hydrogen technologies, which Angel will be speaking about later this morning. We're also looking at liquid air energy storage combined with our supercritical CO2 expertise, the same technology that's in that STEP facility that you'll be potentially see later this afternoon. We're working on advanced turbine development for pumped hydro systems. I think pumped hydro actually is one of the more commonly relatable energy storage technologies. When we have excess energy, we can use that energy to pump water up to an elevated site, a lake, a reservoir of some sort. And then when we want to use that energy, we let that gravitational potential flow through a turbine and generate power. These other thermal technologies are going to use a similar concept, but instead of a gravitational potential, we're going to use thermal storage. So just like you know your coffee cup is warm this morning, we can use that later to let that heat release and generate power. We've looked at system integration and optimization for liquid air. And then what I'm going to be focusing the rest of this talk on, we're working in pumped thermal energy storage. So what is pumped thermal energy storage? It uses two of our fundamental thermodynamic cycles that we are familiar with every single day. The first, in charge mode, when we have excess power, there's too much solar, there's too much wind. We run a heat pump. We take electricity from the grid, we use turbo machinery to create a hot space and a cold space. This is exactly what the heat pump in your house is doing. It's creating the inside of you're using electricity from the grid to make a hot space inside, and actually it's discharging a little bit of cold out into the ambient, whether you know it or not. It's also the same cycle that's running your refrigerator, making a cold space inside. If you've ever felt behind your refrigerator, it's actually kind of warm, right? So a cold space and a warm space at the cost of electricity. Now, when I want to use that hot and cold store, I use the other very common cycle that we know, that power generation cycle, that heat engine. I use that hot and cold reservoir to drive a turbine and get electricity out. This is the same cycle that runs your car, unless you're on an EV. This is the same technology that's running gas turbines and steam turbines. It's the same fundamental thermodynamics. This technology has a lot of benefits. We can store energy for 10 plus hours at relatively high efficiencies. We are leveraging relatively established component technologies that are safe. And the key thing, the economics are beneficial because I can scale my turbo machinery and that rated power separately from how I scale my storage in that duration in tanks of thermal storage. So let's look at what this looks like in hardware. This is an aerial view of the facility we've built here on campus. To give you a bit of scale, you're looking at about 80 feet by 120 feet. Our main working fluid is air. All the white piping is set up as a closed air Brayton cycle, and that communicates with two storage loops. On the hot side, we're using a thermal oil up to 350 degrees Celsius, and on the cold side, we're using a water glycol mixture down to -10 Celsius. So let's walk through how we use this. We're going to run in charge mode. We're going to run the air system in one direction, bring power in from the electricity grid, and create a hot and cold store. Now, when we want to use that energy, we'll move to discharge mode, run this system in the other direction on the air side, pull that hot and cold in from our storage, that thermal energy that we've stored, and produce power through a heat engine cycle. So the hardware that we're using to do this, we have two turbo machines, a compressor and a turbine set, one for charge mode and one for discharge mode. These machines are custom SwRI designed radial machines for this specific application. The radial impeller that you see there in the picture is about the same size as this one that I've got with me today. So relatively small machines for this small scale demonstration. These machines are connected to 8-inch piping, the white piping, and valving that connect to heat exchangers on both the hot and cold side and communicate that heat back and forth to the two thermal loops, where that hot and cold energy is moved between two tanks in each storage system. All right, so this project was funded by the US Department of Energy. We've just completed a nearly 4-year period of performance with for about a project budget of $3 million. We developed this kilowatt scale, so about rated at 5 kilowatts and 1 hour of storage, a small scale demonstration to be a first of a kind. Its full scale commercial version would be a 100 megawatt, 10 plus hours of storage. Our facility sits on about a 1/4 acre, so roughly a standard residential lot. The full scale version would be about 10 acres. Our machines are very small relatively small radial machines. The full-scale system will leverage the largest axial machines that we have in existence today. SwRI was the lead on this project. We did the design, the assembly, and the testing for this facility. And then our project partner was Malta. They're the commercial developer for the full-scale technology and advised on the techno-economics and the translatability of our lessons and test matrix to the full-scale system. Our goals were aimed at first implementation challenges and controls and operability at this small scale for the full system. So what have we accomplished? We made it through our key objectives. The first one being we did it. We have a first-of-a-kind air thermal energy storage system. It pumps heat, it stores it. Second, our test matrix executed numerous different controls and operability tests. We looked at thermal ramp rates on the individual components. We managed system balance as we moved from charge to discharge to charge to discharge mode between all of those tanks. And finally, arguably the most important, we've been carefully documenting with our project partner the various lessons learned through the challenges and the respective solutions along the way, making sure that everything that we've learned here at SwRI can be translated to the outside world and implemented as we take these technologies, as others take these to commercial technologies. So what's next? Well, we've already actually completed one project where we looked at integrating what it would be to integrate a full-scale pumped thermal energy storage system at a gas-fired peaker plant in a high wind penetration market here in Texas. What do the economics look like? What does that dispatching look like? Secondly, we are in the middle of completing a commercial study with EPRI, where we've hosted a site visit to give a tour to many of their members. The tour consisted of over 20 people. Their members are utility companies. We had people from Canada, the US, of course, and Japan. Everything from CPS, Southern Company, Duke Energy, LA Department of Water and Power. And then actually just last week, we completed a data set for this project itself. And finally, we've got other proposals in the work. There's options to do facility upgrades to expand capabilities. There are options to expand the test matrix that we've already looked at, as well as work through other component technologies. So this project used both my and the machinery department's core competencies to make a first-of-a-kind long-duration energy storage demonstration that will potentially be a step forward in how we make a more sustainable power grid in the future. If you happen to go on the tours later today, when you go to the STEP facility, if you peek out back between the trees and the cooling water tower, you might get a little glimpse of our facility. So thank you for letting me share with you today about this project.
All right, thank you, Natalie. We have a couple of minutes for questions. Yes, David.
I'm interested in, you say that you used air as the fluid in the pipe. Why air?
Correct. So the question is regarding air as the working fluid in the main piping. And there are 4 pumped thermal energy storage as a technology. There's actually 3 versions of it. There's a version that uses air as the main working fluid, a version that uses argon as the main working fluid, and a version that uses supercritical CO2 as the main working fluid. Air and supercritical CO2 are the only ones that currently have people trying to commercialize those technologies. Air just happened to be, we partnered with Malta, and that is what their full-scale demonstration is. We do have other component development projects that are working on SCO2 component developments for pumped thermal energy storage. So we are working in both of those spaces for this technology.
One more question. Alan?
What was the storage capacity of the, pilot plant that was co-located with the fossil fuel generator?
Certainly. During that study, we looked at both 10 hours of storage. We also looked at what that economic benefit of going up to 20 hours of storage would be. Other things that allowed us to look at some key aspects of modularity, we also, because wind is such, I don't know if you're familiar with the power, our peak power demands tended to be about 4 to 6 hours in the afternoon in the summer when just prices of electricity skyrocket in Texas. There's not wind, wind is at night, so you charge. So actually the beneficial arrangement was to have a very long charge and then to be able to dispatch as much power in a very short period of time. So it actually became, we only ever needed 4 to 6 hours of storage for discharge, but we wanted twice the power. So we looked at arrangements that had 2 discharge trains and only 1 charge train, and then looked at also the sensitivities of scaling up to 20 hours of storage on that side. So interesting modularity ability for a specific use case.
Thank you, Natalie. Dr. Smith will also be at lunch today, so if you'd like to follow up with more questions, please seek her out. Thank you.
Thank you.